Good morning, good afternoon, or good evening, everyone. Welcome to another RTDS Technologies webinar. My name is Katie Sidwell, and I'll be your host and moderator today. Our topic for today is very exciting. We're talking about the GTSOC, or Gigatransceiver System on a Chip, which is a new tool for black box control integration with the RTDS Simulator. We have a special guest today. We're presenting this webinar with SMA, a leading inverter manufacturer. So you'll get to hear a little bit from them on the vendor side perspective in terms of implementing their controls on the GTSOC while protecting their intellectual property. Before we jump in, I'll just start with a couple of housekeeping notes. If you're not familiar with our webinar platform, take a look now. The most important tool for you is the Q&A widget. So we really encourage you to ask questions throughout the webinar, and we will address them in the live Q&A session, as well as answering them via text throughout the presentations. Don't ask them in the chat. Please reserve the chat for just introducing yourself, letting us know where you're joining us from. We'd love to hear from you there. But ask your questions in the Q&A. That way we can keep track of them and make sure we provide a comprehensive answer to everyone. Also, if you want the slides for today's webinar, they can be downloaded in the handouts section, so look for the PDF of the slides there. And as well, this session is being recorded and it will be available to watch on demand right away. So if you want to recommend it to a colleague, or if you want to reference this webinar later on, we will email you the link to the on-demand version right after the webinar concludes. In terms of the agenda for today, I'll begin with a 10 or so minute presentation talking about the motivation for developing the GTSOC. So what the relevance is of integrating vendor controls into the real-time simulation while protecting their IP. And then I'll talk about how it works. I'll show you the hardware platform and talk a little bit about how the component works and the workflow, how we see this being used by our customers. Then I'll turn it over to SMA, and Chris Hart from SMA will present for about 15 minutes on their inverter offering, on their existing testing approaches for their inverter suite, and then he'll talk about the vendor side of the GTSOC process. So we worked with SMA to implement their inverter controls on the GTSOC in the real-time environment, and he'll comment on that from his side. Finally, we'll pass the microphone to my colleague Sumek Elimban. Sumek will have the largest part of today's webinar. He will do an in-depth demonstration showing a simulation on the RTDS that involves the SMA controls on the GTSOC, and he'll show you the fact that the controls are fully black boxed and the user cannot access them. So let's get started. We won't be going into much detail in terms of background on the company and the RTDS Simulator today. But if you're not familiar with us, we are headquartered in Winnipeg, Manitoba, Canada. We're very much covered in snow right now. We pioneered real-time power system simulation in the late 1980s. And today, our product, the RTDS Simulator, is the industry standard for real-time simulation and hardware-in-the-loop, or HIL, testing. It's primarily used by utilities and system operators, manufacturers of protection and control equipment, research and educational institutions, and power system consultants. Today we're focusing on black box control in the context of renewable energy, but if you're interested in how this technology can be applied to other application areas, I highly recommend you check out our website or our huge library of previously recorded webinars at the RTDS YouTube channel. You can learn about microgrid testing, IEC 61850, cybersecurity, so go check that out. The unique ability that real-time simulation provides is the ability to do closed-loop or hardware-in-the-loop testing of power system protection and control equipment. So like the diagram shows here, you are connecting your device under test to a simulated network, and you're not only sending signals from the network to the device, but also interfacing the device's response back into the network. This allows you to test multiple devices and indeed entire interoperating schemes at once. It allows for a much more detailed system representation than other testing tools provide. For example, we can model power electronics at a very high level of detail, including switching in the 150 kilohertz range. And it provides unique insights on interactions and dependencies that traditional modeling and testing could be blind to. So we are seeing not only electromagnetic transient simulation, but real-time electromagnetic transient simulation become a much more common part of the utility's approach to technological readiness. As grids become more complex, and particularly as power electronics become a dominant form of interfacing generation to the grid, and HVDC becomes much more common, this type of testing becomes more and more critical to accurately predicting outcomes in the system. De-risking renewable energy integration is one of the main contexts where we see black box control simulation for the RTDS Simulator being useful. So I just wanted to touch on these applications. DER integration studies can be small or large scale. Often they're done by utilities or system operators who are looking at how large planned quantities of renewables will affect their grid, or looking more at a single plant installation, looking at how the renewable energy will potentially interact with other technologies on the grid, such as existing protection and automation. Replica testing is very established in the HVDC and FACT space, where the utility receives a replica of the HVDC controls cubicles, which then live in a lab connected to an RTDS simulator modeling the grid for testing. And we're starting to see interest in this for large DER plants as well, where a lab-housed replica of the DER controls would allow the utility to speed up the commissioning process, conduct tests that aren't convenient or possible in the field, troubleshoot, and de-risk any changes through the project lifetime, either to the control strategy or to the network. So why bring OEM black box control models into these renewable energy applications? Well, generic models do not always suit the purpose. Depending on the phase of testing and the phenomena of interest, whether the user is concerned about potential interactions in the system, they may want to go a step further than the generic model and have a detailed, accurate OEM control model involved in the simulation. So in those cases, the vendors need a way to provide those models while protecting their intellectual property. This concept is very established in offline EMT simulation. So most vendors have a black boxed PSCAD model of their controls, which they can provide to utility customers. So in the case of a new DER project or a power plant controller installation, the utility requests that model from the manufacturer, and they can then integrate that model into their PSCAD grid model for testing. So what we're talking about today is taking this concept and bringing it into the real-time environment so those black box control models can run deterministically in real time as part of the real-time simulation and therefore be part of a hardware-in-the-loop testbed. But there are some significant implementation challenges to do this. So over the past couple of years, we've been working on this, and the solution we're presenting today, the GTSOC, successfully addresses many of those challenges. One way to look at black box control simulation is as filling a gap in this progression of testbed complexity when it comes to testing power system protection and control equipment. So on the low hardware involvement end, we have offline simulation, where the utility has a PSCAD model built up of their grid. They're simulating it on the PC. They might have some OEM controls integrated, black boxed in the PSCAD DLL files, but there's no hardware involved in the testbed. On the more complex side, you have replica testing, control hardware in the loop testing, and even power hardware in the loop testing, where the utility might be testing inverters to characterize their response to faults. Black box control simulation comes in where those question marks are. It allows for accurately studying interoperability in the HIL environment without requiring all physical control hardware to be present. So if a utility is installing a large-scale inverter nearby to series compensated line protection, black box control simulation allows them to get the detailed behavior of that inverter controller without having the actual controller present or the inverter. So it's reducing hardware complexity, and it's a very convenient solution. The platform we've developed for this, which we are showing you today, is called the GTSOC, or Gigatransceiver System on a Chip. This box features an FPGA board with multiprocessor system on a chip technology, ARM cores, which are specifically targeted for vendor black box control modeling. If you're familiar with our existing GT FPGA unit for the RTDS, this will look very familiar. It has the same form factor, but it does have that addition of the ARM cores inside the box. The GTSOC supports execution of static library .A models, which are compiled from the original vendor control source code. And it's compatible with NovaCore systems only. It's connected to the NovaCore chassis via fiber cable. So unfortunately, the GTSOC is not compatible with PB5 or prior RTDS systems. In developing this solution, we looked at several different static and dynamic library file options, and we selected the .A because it runs bare metal without an operating system on the ARM core of the GTSOC. This allows us to integrate it with the real-time simulation running on the parallel processing hardware via fiber cable without worrying about a Windows OS presenting difficulties with deterministic operation. This slide gives you an idea of capabilities. We have a look at the GTSOC in the bottom left of this slide. You can see that each unit has 4 ARM cores, and each of those cores can support up to 5 .A instances simultaneously. So that gives you up to 20 .A instances per GTSOC board. Now, these can be identical controllers or different, but this quantity of 20 highly depends on the complexity and the time step of the controls. So if you were to run highly complex controls that you wanted to keep at a relatively low time step, the number of instances might be reduced. The .A's running on the ARM cores communicate with the NovaCore chassis via the FPGA, which we call the RTDS interface. And on the right-hand side, you can see the RSCAD component for the .A instance. Each instance has a maximum of 64 control inputs and 64 outputs. And you can see the time step is displayed there in the component. The time step of the controls is user definable. I believe we've worked with time steps in the range of a couple of tens of microseconds up to 150 or 200 microseconds or so. When it comes to the vendor side of cross-compiling their existing code into the .A and furthermore into a GTSOC firmware, we've created this GTSOC interface tool. You can see the GUI here on this slide. This program accepts the vendor's C code, cross-compiles it to the .A, and generates a firmware to run on the customer's GTSOC. A wrapper is also created, and that wrapper code is what maps the controller inputs and outputs to signals in the RSCAD software. Sumek will talk more about the firmware generation process and the wrapper in his demonstration shortly. We have successfully worked with a few vendors now to implement their controls on the GTSOC, including SMA, who will present right away. And we're currently working with the OEMs on a case-by-case basis when it comes to implementation. Because the technology is fairly new, we've been supporting the cross-compilation process and the wrapper code generation process. But in the future, vendors will be able to create these models and the wrappers independently and automatically. The GTSOC interface tool that I just showed does not require an RTDS simulator to run. So it's not necessary for the vendor to have a GTSOC or even an RTDS simulator to create the model using the cross-compiler. So far, we found that it's very helpful for debugging, but the idea is that any vendor will be able to open up that GTSOC interface tool, cross-compile their code and create the GTSOC firmware, send those to the customer while protecting their IP. We are definitely seeing an interest and a demand for this technology from our users, so we're really excited about the GTSOC and the opportunities that it presents. All right, without further ado, I'm happy to introduce Christian Hart of SMA, and then he'll turn it on over to Sumek for the demonstration. Enjoy.
Thank you very much, Katie. Welcome on behalf of SMA Solar Technology to the webinar SMA Sunny Central Inverters in RTDS. My name is Christian Hart, and I'm currently in the position of a system architect in the business unit Large Scale and Project Solutions. After the usual greetings by our legal department, a couple of numbers about SMA for those of you who don't know us. SMA was originally founded in 1981 by 3 graduate students from the University of Kassel in the center of Germany. Already back then, the 3 gentlemen had a clear vision that the future of the world's power supply technology has to be based on renewable energy sources. A bit more on SMA's innovations and developments over the years will follow on the next slide. With more than 35 years of experience in systems technology for PV applications, over 3,500 colleagues worldwide, 113 gigawatt of installed inverters, of which more than 40 gigawatt are Sunny Central type inverters for utility scale projects, SMA is a strong partner for projects. As mentioned before, the headquarters is located in Kassel, Germany, but we do have many subsidiaries all over the world. The history of SMA goes way back to the year 1981. After first years already developing control systems for wind-diesel hybrid systems in Greece, SMA developed the first transistor-based inverter for photovoltaics that went into serious production in 1987. Fun fact, some of those inverters are still in operation. That's quite a testament to the quality. But eventually it would take some years until the photovoltaic market really took off and further innovations would pave the way to where it is today. A couple of these innovations and products can be seen along the timeline. Just to highlight 2 from the business unit I'm working in 2010 SMA released the Sunny Central CP inverter, one of the most successful central inverters worldwide. And in 2019, the Sunny Central Up family entered the stage, the inverter I'm talking about today and how it can be represented in RTDS. Well, let's take a closer look to this one. Sunny Central Up is a family of inverters sharing the same hardware and software platform with minor variations. This makes it very convenient to realize different types of applications. Efficient conversion of solar power is done by the classical Sunny Central photovoltaic inverters. With a true DC input range of up to 1500 volt DC and a power rating of up to 4.6 megawatts, it's really a workhorse in solar power generation. The second member of the family is the Sunny Central Storage Up, a bidirectional battery inverter capable of working in traditional grid following mode as well as in innovative grid forming mode. 100% grid independence by completely going off-grid is no problem, and adding services like synthetic inertia or additional short-circuit current contribution provides benefits for safe and stable operation of grids. The latest family member is a specialist in power conversion for hydrogen applications. The SMA Electrolyzer Converter Up is a grid-friendly rectifier for powering various types of electrolyzers. For those of you who have never seen a central inverter up close, here are some open doors impressions of the PV inverter variant. The right-hand picture shows the DC compartment with the PV input fuses and 3 DC contactors. The open compartment to the left of the operator's panel hosts many of the printed circuit boards for the control of the inverter. Underneath is the cooling air outlet. The left-hand picture shows the AC compartment. In the middle are 3 power electronic stacks operating in parallel. AC filter and circuit breaker are hidden behind the doors at the bottom. On the front, we can see the AC connection terminals to connect the medium voltage transformer, stepping up from around 600 volts to 690 volts to whatever medium voltage is required for the project. Even within the group of a family member exist variants concerning the power rating or the DC input voltage range to perfectly match project-specific requirements. But all devices share the same electronic control boards and core of the control software. Here we can see the main types of Sunny Central storage and PV inverters in the SMA large-scale portfolio. Testing the performance and behavior of our equipment is a serious topic for us. I would like to share with you a couple of impressions from our test labs and show that a lot of knowledge, equipment and effort is needed to reach and maintain high quality standards. So here you can see the test chambers for the equipment under test. This is an example how it looks inside such a test chamber. We can see cooling equipment for heat dissipation. Of course, we need additional equipment for power supply on AC side and DC side, and for measurement. And we use our inverters as DC sources or AC sources with a variable grid voltage and frequency. SMA does also run a very large EMC chamber for testing electromagnetic compatibility, climate chambers for extreme temperature conditions, and of course an outdoor test field with a PV installation. You can spot a little bit of the modules in the background. So as we can see, a lot of equipment is involved in testing the inverters, but not all tests require the presence of the full hardware. Many tests cover software and control-related topics. That's why we are also running hardware-in-the-loop systems that involve our control boards running the real control software. The heavy hardware and surrounding environment like DC sources, the AC grid, and everything in the powertrain of an inverter is emulated by a simulation system that stimulates our control boards. The left card hosts the control boards of 3 inverters. Marked in yellow are the ones belonging to one inverter. The right-hand card contains the power electronics boards. So here again in the block diagram view, the powertrain of an inverter is modeled on a real-time simulator platform. Inverter and plant control units are real SMA equipment connected to I/O interfaces of the real-time simulator. That's a really excellent setup for us to do qualification tests or firmware validation, and even integration testing with customers' equipment, which is something we offer as an engineering service. But sometimes people are just interested in the control behavior of our equipment rather than having the physical device available at hand. A typical application case, for instance, is a customer designing a microgrid, maybe with Sunny Central storage battery inverters, maybe in grid-forming mode, being the only voltage source forming an isolated grid. And then he wants to test the behavior of his real physical protection relays. He wants to know how to tune and parameterize his protection settings to handle fault conditions. So at this stage, the customer does not need the presence of the real physical SMA device, but is interested in having the original behavior as close as it gets, and of course in real time in order to stimulate his protection relays. Normally this would require us to remodel our inverter control system in the native development environment of RSCAD. But today's inverter controls are so complex and cover such a wide variation of applications, as I have shown earlier with the family of Sunny Central Up inverters, that it is a huge effort for an OEM to develop and maintain such a model over the full production and maintenance cycle of an inverter. And so RTDS has approached SMA if we would be interested to try out to extend the scope of the real-time simulator by giving the possibility of an easier integration of existing control algorithms into the RTDS environment. The exact steps on how to do that with the GTSOC is being described by RTDS. But what I can do is show the process at SMA, how we create the code that is included in the library for the GTSOC. The starting point of the process is an executable specification that contains the inverter's control, operational control, grid integration, protection, and diagnostic functions. It is a common model our control system engineers and model-based software developers are using to immediately test new ideas and requirements. By means of target-specific code generation, it is convenient to generate C code for either the real firmware that is deployed to the inverter hardware, or a library that can be included in PC-based electromagnetic transient programs like PSCAD EMTDC, EMTP, Power Factory, and ATP. Such programs are widely used for doing grid integration studies. Also, this code can be integrated into a .A library for the RTDS GTSOC hardware. A demonstration of the capabilities of the GTSOC will be given by RTDS afterwards. At the end of my presentation, I would like to give a little demonstration of our RTDS hardware-in-the-loop system. The test setup consists of a Sunny Central storage inverter in grid-forming mode, performing a black start of a microgrid. In the runtime view of RTDS, we can see a simplified visualization of the inverter and its internal switches. The states of the contactors and breakers are shown, as well as measurements of active and reactive power and the AC voltage. The battery is represented by a simple voltage source and a resistance. A Y-delta transformer grounded on the medium voltage side steps up the AC voltage and is supplying a resistive load. For a second test, we added a button that creates a temporary single phase to ground fault in order to show the write-through performance of the inverter in grid-forming mode. At the bottom, you will later see voltages and currents at the terminals of the inverter. In order to start, we first have to go to the user interface and set the operation command parameter to grid-forming mode. I quickly switch over to the overview panel since everything is happening in real time so fast. We can see the DC contactors and AC breakers closing, and the inverter is supplying a load of 870 kW in grid-forming mode. Please note, the DC current measurement is not yet calibrated in our system, hence there is a large deviation between AC and DC power. Now let's have a look at the same procedure from point of view of the RTDS runtime. The inverter is still stopped, thus the voltage and current signals only show some noise. We can see how the inverter is pre-charging its DC link from the battery, closing all relevant contactors and breakers and supplying the load. After a couple of seconds, RTDS updates the voltage and current plots, and we can see how the voltage is ramped up from 0 volts to nominal voltage. And here in a zoomed-in view. In a second test, we now push the red button in order to create a short single phase to ground fault on the medium voltage side. After a short time, RTDS updates again the measurement plot, and we can see how the inverter rides through the fault, supplies a fault current, and recovers after the fault has cleared. So, to conclude this presentation, we learned that hardware-in-the-loop systems significantly simplify the testing of complex systems and thus help to improve quality and reliability of our inverters. Definitely not all tests can be carried out with real-time simulators only, but a lot can be done, and that reduces testing time and thus development and machinery cost. Besides that, RTDS created with the GTSOC hardware an easier way for OEMs to include their real control algorithms into the RTDS simulator in a black-boxed manner. This is giving customers an excellent real-time tool to study the performance of equipment in the specific context of their projects. At the very end, I would like to thank RTDS for giving me the opportunity to talk about our products and what we do concerning testing. And I would like to thank you, our audience, very much for participating in this webinar.
Thank you, Christian, for your presentation. My name is Sumek Ellenbad. I'm an engineer at RTDS Technologies, and I've spent a good part of the last several years working on integrating OEM black box controls with RTDS. GTSOC is an exciting new hardware platform to support interfacing OEM black box controls in a software-in-the-loop application in real time. I will provide a demonstration of running the SMA inverter control system on the GTSOC hardware. Before we start the demonstration, I would like to provide a little bit of information regarding the procedure from taking the source code of the controller and generating firmware that will run on the GTSOC. The procedure involves two main steps. The first step is to compile the source code to a static library.a file. This .a file is specifically targeting the ARM cores on the GTSOC hardware. As a .a file, the code is secured and its IP is protected. Once the .a file is successfully created, the next step would be to create the application. The application is the main program which runs on the GTSOC hardware. This is a wrapper program which maps the controller's inputs, outputs, and parameters to signals from the RTDS simulator. As well, the application will also call the main controller step function. On the right here, you can see the main tasks of the wrapper code. So when the simulation starts, it starts off with an initialization function, where code required to initialize the controller can be included. From there, it is followed by a parameter function, where any of the controller parameters that the OEM makes available can be updated. I will provide some more details on this later, as this feature is still in development. After this, it goes into the main while loop, where it will run every sampling time and perform three main tasks. The first task is to receive the incoming data from the Nova Core and map this data to the input of the controller. The second task is then to run the actual controller code from this step function. And the third task is to map the output data of the controller to the outgoing data sent to the RTDS. It will run in this while loop continuously until the simulation stops, and then the interface will be terminated. Once the application code is successfully created, it can then be built into an executable and eventually generating the firmware which will run on the GTSOC. As Katie introduced in her presentation, a GTSOC interface tool has been developed and designed for users to build both the .a file and generate the firmware. The firmware is actually created by the Vitis software development kit from Xilinx. Therefore, it is required to download this software for this step. A link to the download is provided in the documentation. The Vitis software will actually run in the background of the GTSOC interface, and therefore the users do not have to work directly with the Vitis software, which will make the process more user-friendly and the steps as simple as possible. Due to time limitations, I cannot demonstrate the full procedure of generating the firmware. However, I will open up the GTSOC interface tool to provide an introductory overview. So if I exit the presentation, you can see I have the RTDS GTSOC interface tool open. There are four main tabs. We have compile library. This is the first step and generates the .a file. We have generate firmware. This is the second step and includes both creating the application as well as eventually building the firmware. We have a settings tab and we have a help tab. If I select help, I go to help manual. You can see that the interface tool is fully documented. Even though I can't demonstrate the full procedure of generating the firmware, I will demonstrate how to generate a .a file. As an example, in this folder, I have source code of a StatCom controller. This controller was developed in MATLAB Simulink, and the embedded coder tool was used to generate the source files. So I click the folder. You can see I have the C code as well as the supporting header files. So I will use the GTSOC interface tool to cross-compile this code into a .a file. So I'll go to compile library. I'll go browse. And you can see I'll have to find the path of where my source files is. The default path is already correct. So I'll select all the C code files. I will select open. So now the source files are imported. And I simply click compile. If it's successful, it will generate my .a file. You can see it was successful, so it's generated my .a file, and then it asks me where I want to save it, which I'll keep in the same folder. So I'll select save, and then I'll open up the folder again. You can see I have my .a file. So that completes the first step, and then the second step would involve now creating the application. So then I would go to the generate firmware tab, and then what I'd have to do is I'd have to create a new project, and from there create a new application, and within there is where I would create my wrapper code. I would import my .a file, and then eventually I would go through the steps of building the firmware. So we won't go through that procedure during this webinar, but this is a general idea of the steps involved. So this, like I said, this GTSOC interface tool is meant to be user-friendly and to try to make the procedure as simple as possible. So then next, we will then go to the actual SMA demonstration. In this folder, I have firmware for the SMA controller that will run on GTSOC. This firmware was successfully created by working with SMA, which involved both jittering the .a file and then successfully creating a wrapper and eventually the firmware. So this firmware represents one inverter controller for each ARM core on the GTSOC. So there are 4 ARM cores on one GTSOC hardware, and therefore one GTSOC can represent 4 individual inverter controls from SMA. So then the next step will be to take this firmware and load it onto the GTSOC platform, which can be done through the firmware upgrade utility in RSCAD-FX. So then I will copy this folder and I'll move it into the firmware folder in RSCAD-FX. And I'll paste it, and then I could open up RSCAD-FX and load it onto the GTSOC. Before I get there, I'd first like to show what the hardware setup looks like. So open up an image of the hardware setup. On the left here, I have a picture from the front. On the right, I have a picture from the back. So you can see here from the front, we have a NovaCore chassis on the bottom with the GTSOC hardware sitting on top. So the GTSOC communicates with the NovaCore via fiber, and each ARM core on the GTSOC has its own separate fiber connection to the NovaCore. So since there's 4 ARM cores, we have 4 fiber cables connections. So on the GTSOC, there are 8 ports, and we're using ports 1 through 4 for communication. And they can connect to any of the GTIO ports 1 to 20 on the NovaCore chassis. That's simply all that needs to be said about the hardware, and then I'll open up RSCAD to continue the demonstration. So open up RSCAD-FX, which I already have open, and then I'll go to my user directory and find the demonstration case. So SMA_battery_60 Hz. So before I provide a description of the draft, let's first launch the firmware upgrade utility to see how we actually load in the SMA firmware. So I'd go to GTFPGA. So within RSCAD-FX, the GTSOC will be referred to as GTFPGA. You can see I have 1 here. And then I would go to firmware, and you can see I have the SMA firmware. In addition, I have also another firmware. This was firmware that was developed based on the STACOM example that I provided earlier. So I would select SMA firmware, and I would select update, and it would load on there. I'm not going to go through that because the firmware is already loaded onto the GTSOC. So I'll go close, and I'll also go to config file editor. And if you go to the rack I'm using, if you go to I/O ports, you can see that from the NovaCore chassis, it sees 4 GTFPGA units. This is because on the GTSOC, each ARM core has its own fiber connection to the NovaCore chassis. So therefore, the NovaCore will see that as 4 individual GTFPGA units, even though there is only one GTSOC. So I'll just save, sure, and I'll cancel. Okay, let's take a closer look at the draft case. So this case models 4 SMA inverters, which means we also are modeling 4 SMA controllers on the GTSOC hardware. So this is a test case. So the way this circuit is modeled, inside here we have a circuit with 1 SMA inverter, and then we copied it 3 times to have 4 identical circuits. So with the other 3, we just created, changed the names to make them unique. So if I click inside here, you can see the circuit. It's fairly straightforward. So if I go here, I have my AC grid. I have a fault component at the point of interconnection. I have a transformer here to step it down to medium voltage. A pi section model to represent a very short line. Another transformer to step it down to the ratings of the inverter. This transformer also includes scaling to scale the power output to represent a larger farm. So then on the inverter side, we have the filters. So we have our capacitor filters. Our RL filters are inside our inverter component, and we have some breakers. So here we have our UCM two-level inverter model, and then so that's converting the DC to AC. And then on the DC side, we have this is a battery case, so we've simplified the battery to just a DC source. We have some inductors, and then we have a breaker on the DC side as well. So these, so like I said, in the other hierarchy box, we have the identical circuit, just changing the names. So this is just to test all 4 SMA inverters controls on GTSOC. So one thing is for this case, we are the UCM model or inverter models in modulation waveform mode. So we're modeling an average model type model. The GTSOC controller provides their duty cycle as inputs, which is eventually the modulation waveforms. So we feed those signals directly into the UCM inverter. If the end user wants a switching model, that is also okay, but we recommend that the firing pulses are generated within NovaCore, because we want to use our improved firing pulse algorithm to make sure that the firing pulses are more accurate. So yeah, but so because this is an average value model, we're actually running the whole circuit in our main time step. So we're not using the sub step for this case. If you were to, so I would just recommend that you would just consider the application to see if a switching model is required, because maybe a modulation waveform might be more than suitable for what you're trying to accomplish. To interface to the SMA controllers running on the GTSOC hardware, we use the .A component shown here. So this .A component represents an interface to one of the ARM cores on the GTSOC hardware. So since we have one SMA controller running on each of the 4 ARM cores, we have 4 .A components, one for each core. You can think of each ARM core as effectively an I/O card. So we can see we have a port number here. So we have port 1, port 2, port 3, and port 4. So from the .A component, we configure the input names, the output names, and the general parameters of the component. So if I double click on here, I will talk about some of the key parameters. So we have, like any RSCAD component, it needs a unique name. The second parameter here is the execution word. So each controller running on the GTSOC hardware needs to be enabled, and that enable signal is actually coming from RSCAD. And we specify it here, and it looks at a specific bit. If that bit is 1, it means that it's enabled and it can run. As was discussed in the intro presentation, each core can run as much as 5 individual controllers. And each of those 5 controllers will be separately enabled. So if you look at this control word, it looks at the first 5 bits. The first bit will control instant 1, the second bit will control instant 2, and so on. So in the case of the SMA example, since we only have 1 controller running on each core, we're only looking at the first bit. When that bit is a 1, it means that the SMA controller is enabled and can run. So here we've specified 1 instant. Here is the .A simulation time step, which is effectively the sampling time of the controller. This will come from the OEM. So from the SMA controller, it's 166.67 microseconds. And like I mentioned, we have our port number. If we go to configuration, here we just specify the number of inputs, which is 25, the number of outputs, which is 9. So inputs here meaning data going from RTDS to GTSOC, and number of outputs is data going from GTSOC back to NovaCore, or the RTDS. So I have 25 here, and if I go into .A1 inputs, I have to specify the names of all 25 inputs. So the inputs here would be voltages and currents from the system, from the inverter side, the medium voltage side. There are some from the DC side, and then we also have reference signals from our SCAD, so P reference, Q reference, other references as well. And then we have our output. So we have these are signals coming from GTSOC to the NovaCore. So the main ones here are our modulation waveforms. So these get sent directly to our UCM component. We have 4 breaker control signals. We have a frequency measurement signal from the GTSOC. And we have an enable PWM, which in this case it's an average value type configuration we don't use. And then here we have the .A wrapper ID setting, which at the moment we're not using it at the moment, but it's actually a very useful setting. So when in the GTSOC interface tool, when the firmware is created, it needs to be set up with an ID number. And so that number will be hard-coded onto the firmware. And if we're using that specific firmware, you have to match the ID number and set it here. And when we actually run the case, it will compare the value that you set here with what is currently on the firmware. And if they don't match, it will not run. And this is very useful because essentially it's an error check to make sure you're running the right firmware. And it's useful to the end user because they're might be getting firmwares from different vendors, and it gives them, this is their way of identifying each one. So if you go to each one, it's set up in the exact same way. So the same idea. So we have all identical. So just below the .A component, you can see the D block configuration. So I have one for each of the .A components. It's quite simple. When I push the button, this flip-flop will go to 1. So this word here is our execution word. So it's a 1 that gets sent to the GTSOC, and it'll be it's like a notification that the controller is enabled and can run. So if these buttons are not pressed, it means that controller is not active. So before I compile and run the case, I would like to spend a little bit of time discussing controller parameters. Having the ability to change controller settings is very important, because for different projects, you might need some different settings, and we don't want to have a new .A file for each project. So the ability to be able to use the same .A file and be able to change parameters is quite valuable. So this is very common in, say, a PSCAD model where you might have a DLL, and then there'd be some sort of text file where the end user can adjust different settings like ratings, limits, modes. So we know we have to be able to support that. So right now, that is something that's in development. So right now, the .A file here has all the parameters hard-coded. That being said, I can show you what the plan is. So if I double-click on the .A component, if you notice there was a parameter here called import .A parameters from text file. So right now I have it set to no because it's not supported. But eventually, if we were to select yes, we can import a text file. So this text file will have a specific format. We'll have 2 columns. The first column will be the name of the parameter. This is just more of a description. We don't actually use it. But the second column will have the corresponding value. So that value will be used. So when we compile the case, that value will be included in our download file, which can be read by the GTSOC and can be used in the wrapper code, and then those parameters can be mapped to the parameters of the controller. So that's stuff that's still in development, but I can show you as an example. We've been working with SMA on testing it out. So right now I'll just select this to no. But if you're familiar with the SMA model for, say, in PSCAD, you'll get for example, a configuration file that looks like this. This is their own format, and they've built the infrastructure, or they've built in their PSCAD model, they've built the wrapper to be able to support this format. So this is the format that we don't support. Like I said, we have a format where the first column will be just some name, some generic name or description name, followed by a numerical value. So with working with SMA, what they've done is they've built a very simple program that will take this file and then convert it into the form that we require. So so then they built this program, and then what they've done is they took it and they generated a parameter file that looks like this. And so this is the file that we would support. So for them, they just put a generic name, like an ID name, so parameter 0, 1, 2, all the way down to, in this case, 1023. So for each instant, we'll support the ability to have up to 1024 parameter changing. 124 parameters can be supported for each instant. And so SMA then took their configuration file that they have in PSCAD, and then they create this file. So as the end user, they could simply use this. They can make the changes that are required. They can run the tool that SMA will provide to generate this file. So you can see here we have some values here for different parameters. We use this value right here, 225,99522. That's more like a dummy value, and it's an indication to the .a file that those specific parameters are not to be updated and just use the default. Okay, so with this format, we'll be able to sort parameters. But at the moment, right now, it's not there, but we're hoping to wrap up that thing soon. Now I can compile the case. So I'll press the compile button here. I can see that the case compiled successfully. I can check the hardware allocation. So you can see I'm using 3 cores on the Nova Core, 1 for the network solution, 1 for power system components, and 1 for controls. But for the controls, I could easily stack that on to one of the available cores because there's not much controls, because the main inverter controls are running on the GTSOC. So I could run this case on 2 cores. So then I will go and open up the runtime file. Okay, so I have the runtime file here. If you see here, so the draft case has 4 SMA inverter circuits, all individual. So here I've created a little diagram for only the first inverter with all the meters and the specific buses. But for the other 3 inverters, I'm also just plotting the main signals. But for each inverter, I have the main control input, so I can enable the GTSOC. This is the enable button for the controller code in the .a. I can enable a fault from any of the circuits, as well as the main control modes. So you see for each inverter, I'm monitoring the duty cycle. This is the converter side voltage, converter side current. This is the voltage near the transformer. Here are the other outputs from the GTSOC. So for example, the breaker controls. I have the DC current, DC voltage, and then the scaled up power connected sent to the grid. So I have the same for all 4 inverters. So for each inverter, you can see I'm in, this controls the mode. So here 21416, which corresponds to power control. So each is in grid forming mode. grid following mode. So then if I run the case, so the case is running. You can see I have, this is the power, this is a P and the Q and the Q on the other side. Here's the voltage at each bus. You can see that there's zero power flowing, even though I've enabled the controller from the dot A, but I haven't actually enabled the GTSOC, so it's not actually active at the moment. So then I will deblock it. You can see here, I get now 3.6 megawatts on the inverter side, and then with the scaling I get about 100 megawatts. So that corresponds to 1 per unit power, which I have it set here. You can see here's the deblocking transient from the duty cycle from the voltage. So talking with SMA and showing the results, this is exactly what they would have expected. So right now I've only deblocked inverter number 1. So then I can also block inverter number 2. You can see the same transient. Now this one's hit steady state. And if I wanted to, I could enable both inverter number 3 and inverter number 4. So they're now all sending 100 megawatts. So I could also, there's another example, I can provide a fault. So I'll just provide a fault to inverter number 1. So I'll apply a fault. So you can see here, we have a fault here. Voltage, current, there's the DC current, DC power, and AC power. I could also try to, as another test, I can change the reference mode. So on the first inverter, I can go from 1 per unit down to 0.5. So this input gets sent to the GTSOC. So I should see half the power flowing. You can see now I went from 3.6 megawatts down to 1.8. And on the other side, I get up 50 megawatts into the grid. If I look at the plots, I can see a slight change in the duty cycle. I can see the converter current drop about half. And I can see the DC voltage. So you can see a little bump. You can see the scaled power drops down to 50 megawatts. So then as maybe a final test, I can maybe change the frequency of the grid. So in the controller, SMA said that hard-coded there's a frequency. The first frequency threshold is 60.5 hertz. So if it goes past there for a certain period of time, I forget the number, it will trip. So you can try to test that out. So maybe we'll increase the grid frequency to say 60.3. You can see here. You can see that the GTSOC or the controller measure the frequency of 60.3, which is still below the threshold. So it's still enabled, it's still running. See maybe a little slight transient, but so far it's still okay. I can go up to 60.5. 60.5 is still good, it's right at the limit. One thing, a little maybe slight threshold, but nothing, it's still not tripping. But then once I go past that, so I go 60.6, and then I mean, it's a constant value, so it should hit the time limit. And so it should trip. So if I go 60.6, I go enable, you can see the power went down to 0. And we look at our circuit, the system tripped. Right, and if you can see, these breaker signals tripped. So just as we expected. So what we're seeing here now is, if we kind of wrap up the demonstration, we are seeing the SMA controller running on our GTSOC platform in a software-in-the-loop application in real time. So that's pretty exciting. So that wraps up the demonstration. Thank you for listening. I will pass it on back to Katie. Thank you.
Hello, everyone. Hopefully you can hear me loud and clear. Thank you so much for your attendance today and your great questions. We had a really nice attendance. There's clearly a lot of interest in this topic, and we're very happy about that. So thank you. Let's get to a few questions. I wanted to start with a question about CBuilder or component builder. So RSCAD does have a built-in facility called CBuilder, which allows new models to be created using C code. Either control or power systems models can be created this way. And then they run in real time alongside other models in the library. So the question was, why is the GTSOC needed? Why can't the vendors use CBuilder to create these models instead? The main reason is that the GTSOC is designed to allow the customer to use their original source code, their original code base, without modifications. So CBuilder requires a specific code structure. And in the case of, for example, inverter controls, which are very complex, many different tasks and timescales involved, as Christian mentioned. So being able to use the original code base without modifications is a very key aspect of the GTSOC. So that's the main reason there. Let's move on to a question about time steps. So someone asked, does the .A require a specific solution time step, or are there ways to synchronize and downsample I/O between the GTSOC and the RTDS? Sumek, maybe you could take that question.
Sure. Can you hear me?
Yes, we can.
Can you hear me? Okay. Oh, perfect. Okay, yeah. So that's a good question. I think one thing we have to just emphasize that there will be the GTSOC and the Nova Core can run asynchronously. So the time step running on GTSOC doesn't have to be the same time step running on Nova Core, and that would kind of mimic what it would be in the real world. So in the Nova Core, you can specify what time step you want to run. Let's just say it's 50 microseconds, or for a smaller time step. And then you would specify the time step of the GTSOC, which is essentially the sampling time. So that would come from the vendor on how frequent their controller sampling. So for SMA, their controller will sample at 166.67 microseconds. So then in RTDS, we're not running at that time step. So then we're running in an asynchronous mode. And so essentially what's happening is that in the .A component, I specified that the sampling time is 166.67 microseconds. That gets sent to the .A, and then that gives the .A or the GTSOC of how frequently it will sample. So in the Nova Core, we will just update the data every time step, and we'll send that to the GTSOC. But then the sampling time that we specified in the GTSOC, when it comes time to sample, they will just sample the latest available data. So 166.67 microseconds, it's like, okay, it's a new sample. I'll just get the data, and it'll be whatever the latest thing that RTDS sent. So it's running asynchronously. We don't have to synchronize it, which is okay, because I think that's really what would happen in the real world. So there should be, just want to emphasize too, there's a RTDS time step, and then there is a GTSOC time step, and they don't have to be the same thing.
Perfect, thank you. Yeah, I think that's very clear, Sumek.
Yeah.
Thanks. We have a good question, I think that Christian can answer from Marco. And the question is, Why should I go with the GTSOC compared to asking an inverter manufacturer for a control board with documentation on how to connect it to a real-time simulator? So what's the motivation for using the GTSOC over the hardware in the loop for inverter applications?
Yeah, hello everyone. Can you hear me? Can you just give me a feedback? I'm going
Yep,
through.
loud and clear.
Yeah, fine.
Yes.
Okay, that's actually pretty easy to answer. Typically, such controller boards they are not available for sale. Typically, OEMs like SMA, and I guess that would go for many others as well. They uh, would not release these boards as some kind of a product, because to have such things as a product with all the documentation available for handing out is a huge effort. And that's typically something we don't do. All the boards that we use in a hardware in the loop environment, they have to be modified. If you look at our inverters, for instance, they have a measurement range of up to 1500 volts. So the RTDS simulator, the analog in output and input boards, they operate in the range of 10 volts. So every board has to be modified in the laboratory to be able to be used in a hardware in the loop application. And around that, actually, to put that whole thing into operation, we not only have to send the controller boards, we have to send an engineer as well to to teach you how to do that, and that's simply something an OEM probably would not do.
Yeah, thank you very much, Christian. That's a great answer. And yeah, I think it's certainly possible that for more straightforward applications or for higher level controllers, it might be possible to do the hardware in the loop. But for this specific control type, it's just much too complex and would require much too much modification to make this a product.
Right, Katie. And to add, the idea is to use the synergy of having the same library that you use for Windows-based EMT tools like PSCAD, EMTP, Power Factory, and to apply that to a real-time simulator as well. So in the end, there must be someone behind that over the whole lifetime of an inverter takes care of all these libraries and always updates when there is a new firmware release. And that's something that OEMs need to manage, to be able to manage as well, because that's not our main product. It's supporting the main application, the main product, which is inverter or inverter systems plus plant controller, inverter plus plant controller. But everything that is like used for modeling, EMT modeling or real-time modeling and testing is additional stuff, let's say.
Excellent. Yeah, great point. Thank you. Here's an interesting question, perhaps for Sumek. Does the firmware upgrade tool allow you to download firmwares from different vendors to each ARM core for testing control from different vendors alongside each other on one GTSOC?
Yeah, that's a really good question. So the way it's constructed is even though there are 4 ARM cores and they're very much independent from each other from a simulation standpoint, like I mentioned that they each have their own separate fiber, there's only one, currently there's only one firmware that is downloaded onto it. So, but in theory, that one firmware in theory could have several different vendors on the firmware. So the only limitation is on each core, the sampling time must be the same. So if you would think, oh, I could have one vendor on one core, another vendor on another core, another vendor on a third core, and then I would just have a wrapper. So each core has its own wrapper. I'd have a wrapper for, say, core 1, which would be maybe, let's say, an SMA inverter. On core 2, I could have another wrapper for another vendor. And then once I built that application, I could create firmware, and it would, in theory, have maybe a different vendor on each core. I guess the issue that might come up though is who's generating the firmware. So obviously, and that could create some IP issues. But in theory, you could have different vendors on one single firmware, but we just have to deal with the issue of how the firmware would be created.
Thanks, Sumek. Yeah, that's clear. Interesting question. I think that's all the time we have today. We're at 10 minutes past the hour, so I'm going to wrap it up. Thank you, everyone, again, for all your good questions. We got a few other questions that we didn't speak to, so we're going to release a Q&A document that will answer all of the questions in detail. And you'll receive an email with that Q&A document and a link to view this webinar on demand anytime you like. So don't worry, you will be receiving a copy of this webinar in your email as well. So I want to thank Sumek and Christian so much. This was a really interesting and collaborative webinar. So thank you for joining us, and I hope everyone has a great day.